In this course, we're going to work with a lot of different types of functions. So today's lesson is about just looking at some of the basics of maybe a few functions that you're not familiar with. Maybe you are, but they might be new to you. So let's just go through it. I'm not going to go through the whole note, by the way, today. I've got the way this note works is I'm going to go over some introductory stuff, and then it's really an investigation from there on out, where you're going to fill in some values, create graphs, and just sort of get to know what the functions are like. That will be the homework, so to speak, is just filling in this investigation. So let's get started. So a couple definitions that you need to know. First of all, what's a family of functions? It's a collection of functions that share the same shape and characteristics. So all quadratics, for example, could be considered a family of functions. I guess I could be even more specific and say all quadratics with the same stretch value and so on. Or another family of functions would be all linear functions that share similar characteristics. Now, carrying on the metaphor of a family, then we could have what's called a parent function. The parent is the simplest, the most basic function that the rest of the family is built off of, okay? And so that's what today is about. Today is about parent functions in particular. What are the most basic functions of different sorts? So the good news is we already know a couple family of functions. We know linear and we know quadratic. Parent functions for linear are y equals x. Now I'm using function notation, which you know how it works now. You know that f at x just means the same thing as y. So we could think of this as the same as y at x, what I've just, y equals x, to use some variables that you're more familiar with. So what does a basic y equals x line look like? Well, if we think about it in the form y equals mx plus b, then we know that if it's y equals x, like this, then m would be 1 and b would be 0, right? So it's going to have a y-intercept of 0. It's going to have a slope of 1, which we can always think of any whole number as a fraction as 1 over 1. So we'd start with our y-intercept at 0. We'd go up 1 and over 1, up 1 and over 1, and so on. And that's how we'd get that line. So that's our parent function for a linear function. So that's one we know. The other one that we should be familiar with by now is quadratic. And the most basic quadratic that we can have is f at x, or y, at equals x squared. And again, if we think about the format, maybe the easiest way to think about graphing a quadratic would be a times x minus h squared plus k. So if we have an equation that's y equals x squared, if I was to fill in the different parts, there's no number in front, so it would be a 1, h would be 0, and k would be 0. So we'd get our vertex at 0, 0. It would be opening upwards. It would have the normal step pattern, so over 1, up 1, over 1, up 3, and so on. And again, that's what our most basic quadratic is going to look like. Any members of the family of linear functions can be written in the form y equals mx plus b, except vertical lines. Those aren't functions because, as we know, vertical lines have points with the same x value and different y values, and can't be a function. Any member of a quadratic family can be written in the form, vertex form, as I just showed. So add the following family members to the appropriate graph. So this would be a member of the linear family of functions. I can recognize linear because there's no exponent on the x. Quadratic is going to have the exponent too. So this is a linear. It's got a slope of -0.5, so it's going to have, and it's going to have a y-intercept of 0. So maybe I'll use different colors. So I'll use this green. So y-intercept of 0, slope of -0.5 means I go down 1 and over 2, down 1 and over 2, and so on, until I have enough points to draw my line. which I seem to have here. And so that would be the graph of A. If I was to do B part, that's also linear. I recognize it. It's got a y-intercept of -4, and it's got a slope of 3, which would be the same as 3 over 1. So from -4, I'd go up 3 and over 1, up 3 and over 1, up 3 and over 1. And so again, oops, I went over 2 though, didn't I? Over 1. So I do enough points so that I can draw my line, and I connect the dots, and there's my graph. And x equals -4. Okay, still linear for that one. Let's do this one in purple. X equals -4, you should remember, is just a vertical line. It goes through -4 on the x-axis, and it just has every point on the graph has an x-coordinate of -4, and whatever the y values are, it's going to be the same. That is a vertical line. That one's not a function. It fails the vertical line test, but it's still a member of the family of linear, although not a function. So again, there's 3 examples of linear relations, 2 of which are functions, and they share common characteristics. They all form straight lines. So the next couple are quadratic. I know that because they have the exponent 2. And again, just going back to some stuff we know about quadratics, if I was to do this one, let's say in green, it's got a vertex of +3, +2. So 3, 2 would be my vertex. It's got an A value that's -1, and it's going to open down with no stretch. So over 1, down 1, over 1, down 3, and the same on the other side. And there's my enough so that I can sketch this graph. So this would be part D. And for part F, again, I got a vertex of -3, -5. So that would be down here. And it's got a stretch factor of 2. It opens upwards, and it's stretched by 2. So it goes over 1, up 2, over 1, up 6. And that's all I have room for, but it does the same thing on the other side. There is a sketch of, what is it, E, part E. And again, these 3 graphs you can see are all part members of the same family of functions. They're all quadratics. They all form the U shape. And so, but they're all based off that parent function of y equals x squared. So today we're going to explore 3 other families of functions that we're going to use throughout the course. We're going to look at the reciprocal function, we're going to look at the square root function, and we're going to look at the absolute value function. So just a little bit about each one. The reciprocal function is one that's written as a fraction. Its parent function is y equals 1 over x, or f at x equals 1 over x. So it's always going to be a fraction with the exponent, sorry, not the exponent, the variable on the bottom. Square root function is always going to have we're taking the square root of the variable. We're taking the square root of x. And the absolute value function is one that where we take the absolute value of x. Now you may not know what absolute value is at this point, so let me explain it. You see these 2 lines on either side of the x. They're like brackets, but they mean something in particular. They mean that whatever is inside between those 2 lines is going to be positive. We have to simplify it first, though. That's a big thing to watch out for. So if there's multiple things, if there's operations going on inside those absolute value signs, follow order of operations, simplify them down to a single number, and then make it positive when you take those absolute value signs off. So here's some examples below. So if I just have -7 inside the absolute value signs, there's nothing to do other than take the absolute value signs off, and it becomes +7. If I have -4.32 inside there, once I take the absolute value signs off, then it just becomes +4.32. 0 is still just 0. It's neither negative nor positive. And 4, if something's already positive, like in D part, it stays positive. It doesn't change to the opposite sign. It just becomes positive. That's what absolute value does. Now, just to give another couple of examples to illustrate something that we haven't seen here yet. Again, I have to treat them like brackets. So what if I had -7 plus 4 inside the absolute value signs? I don't change that 7 to positive and then add them. What I do is I simplify what's inside the brackets first. So I do negative 7 plus 4 first, and that becomes negative 3. And then at the moment that I take off the absolute value signs, then my answer becomes positive and becomes positive 3. You can see how I'd get a different answer if I change that negative 7 to a positive at the beginning. I end up with 11, which would be incorrect. So again, treat them like brackets, follow order of operations, and only as you're taking the absolute value signs off, that's when you make them things positive. One more definition, which you may not have heard before, something called an asymptote. An asymptote is a line that a graph gets closer and closer to but never touches. We're going to do a lot of stuff with asymptotes in grade 12, advanced functions, but there's a little bit of stuff to do with asymptotes here in this course as well, so it's good to know it now. Asymptotes can be vertical lines that a graph gets closer to and never touches, or horizontal lines, or even on an angle, although for us in this course we'll only be looking at the vertical and the horizontal ones. So the rest of this, this printout, this lesson, is meant to be an investigation so that you can compare these 3 different functions I just talked about, reciprocal, square root, and absolute value, and get a feel for what the parent functions of these different functions look like. But just to help you get started, this is how it works. So each part's set up the same way. So the first one's the reciprocal function. So first we want to compare it to something. So we're going to draw the parent function of f at x equals x. In other words, y equals x. So the parent function of a linear function we're going to draw on the graph. So I'll just do that now. So remember, that's one that goes to the origin and it has a slope of 1. So this is the function f at x equals x, or y equals x. That's the parent function. And then we're going to, using table of values, just see what the graph of f at x equals 1 over x looks like. So just a little practice working with tables of values. Remember, all you have to do is plug in the x value into the equation to get the y value, or the f at x. So y is equal to 1 over x in this case, right? So when x equals negative 3, y equals negative 1 over 3, or 1 over negative, let me write it this way instead, 1 over negative 3, but usually I always stick the negative sign up top. So those mean the same thing. And that gives me a point, doesn't it? And I'm going to do this in a different color, so let's do it in green. So at negative 3 and negative 1/3, there's a point. And then if I put negative 2 in, I get negative 1 over 2. So at negative 2, I get a y value of negative 1/2. And at negative 1, I'd have negative 1 over 1, which is just negative 1. It simplifies down. So I'd have the ordered pair negative 1, negative 1. So I'm just filling in the table and then plotting the ordered pairs I see. When I do 0, I'd have 1 over 0, which is undefined. So if something's undefined, we can't plot anything there. So I can't put a point there. I can't do the point 0 undefined. That doesn't make sense. So I'll skip over that one for now. But then I have 1 over 1, which is just 1. So I'd have the point 1, 1. I'd have the point 1 or 2 and 1/2. I'd have the point 3 and 1/3, right? So I plotted those points. I can sort of see what's going on, but I don't think I'd be totally confident graphing this yet. I mean, what's it going to look like? Is it going to look like this? I just don't feel like I have enough information yet to graph this. So what I would do instead is maybe get a few more points. Like, what's going on near 0? Say I put positive 0.5 in for x. This is where you got the extra rows for. Well, putting into the little function, I'd have 1 over 0.5. When we divide by 0.5, that equals 2. So when I have 2, so when I have 0.5, I have a y value of 2. Interesting. Does the same thing happen for negative 0.5? Yeah, I get negative 2. Interesting. So I have the point negative 0.5, negative 2. So these two graphs can be going in opposite directions as we get closer to the y-axis. Let's try another one, like say 1/10. 0.1. Well, 1 divided by 0.1, it's supposed to say decimal 1, equals 1/10. Sorry, 1 divided by 0.1 equals 10. So at 0.1, just a little bit to the left of the right of the y-axis, I got a point way up at 10, which is off my graph. So I can see what's happening is I'm getting closer and closer to the y-axis, and I'm never going to touch it. And the same thing's happening with the x-axis. So I can, just to cut to the end result, I would expect you to keep working, on this and keep filling in points until you're comfortable with it, but eventually you'd get, sorry, my iPad is acting up on me. My goodness. Just a second. All right. There we go. So there's our graph. And then we can answer different questions about it. We can say what the domain is of the linear function of the parent one. So we know the domain is all real numbers. And the range is all real numbers. For the reciprocal function, we can see that the domain is all real numbers, it seems, except x can't equal 0, can it? When x equals 0, it was undefined. So since that's the only thing it can't be, I'd put x cannot equal 0. And for the range, it would be all real numbers again. Except again, you notice how it never touches the x-axis. So it's not undefined for the x-axis or for y equals 0, but it never actually touches y equals 0, so I would put that as a restriction as well. And then I can just list, what are the special features I notice about it? Well, again, it's only in if I look at the special features for linear, it's a straight line through the origin. It only is in quadrant 1 and quadrant 3. There are no asymptotes. For the reciprocal function, it's not a straight line. It's in two parts, two pieces for this graph. It is still only in quadrants 1 and 3, though. And there is an asymptote. There's two asymptotes, in fact. Asymptotes are these lines that the graph gets closer and closer to. And so this one gets closer and closer to x equals 0, that's the vertical asymptote, and y equals 0, which is the horizontal asymptote. So, of course, I did this by hand, and, as far as filling in the points goes, but we have Desmos. You can use Desmos as well. You could type in the equation in Desmos and check it out. So y equals x, I can easily see there's the graph. If I did y equals 1 over x, pardon me, well, I try again, y equals 1 over x, then you can see that graph as well. So you can easily fill in you can easily see what's going on here, and I can even zoom out so that I can see that, yes, in fact, it is staying in quad 1 and quadrant 3, and all the features are as I already saw. All right, so your goal, your job, is to fill in the square root function, to square in the absolute value function. You can do that on Desmos as well, by the way. If you find that easier, which you probably do, although it's good practice to use the table of values, then you can just go straight to using Desmos. And there is an absolute value function option on Desmos. Let's see, where's my keyboard gone? Usually oh, there it is. So absolute value, you can see down in the bottom left, just above the ABC, in the very bottom left, it's got an A between the absolute value signs, so you can use that. I'll leave that to you, though. So the homework for today is to do part 2 and part 3, and then there's just a summary where it's all put together at the end, where you can have it all in one place. All right, and that's it. Good luck.